Alright, we're up and running. How is everyone today? That's good.
Physics is no fun.
Physics is no fun. Newsflash. I enjoyed physics when I was an undergrad. I wanted to understand it better, and I never felt like I got it. But I thought it was a cool subject, and it was stuff I wanted to understand.
And I have to ask,
yeah.
as a coder, how much of that did you use in real life?
Well, you don't find, cylinders rolling down inclined planes in daily life. But what I think I found is that, the process of tackling physics problems, of looking at a massless cylinder, an inclined plane, and a block sitting at the bottom, and trying to analyze it is a similar situation in some ways to, I want to write a program that does this stuff, and it's got to interact with this system, and it's also got to take care of that, and just sort of the process of rethinking problems, of identifying, the relevant pieces, and how to split things off, and how to relate it to other things, and so on. All of that I find pretty relevant on a day-to-day basis, and I think a lot of that sort of training and discipline came from all the painful hours of fighting through physics homework, because we had 2 years of physics when I was an undergrad. There was 4 semesters.
Oh, wow. Yeah, I would agree with that. I think it helps you be able to take the stat and differential equations. I think really help.
Yeah.
To help you learn how to build models out of, and quantify things in the real world.
Mm-hmm. Yeah, so it's all good. The main issue I hear from students is just how much time physics takes them to do the homework and then to study, but mainly homework. And I also hear this from a lot of students about math. They get 100 homework problems per homework set, and it just takes a lot of time, and that's time's always the problem.
Well, what do they say for homework? They say for every credit it's like 1 hour per week kind of a thing, right? Or something like that.
So for every hour you spend in class, you're supposed to spend 3 to 5 hours outside. So a 5 credit class is roughly 5 hours a week. So 15 to 25 hours per class outside of the classroom, which is great if that's the only thing in your life. If you're a full-time student, you can do 60 hours a week of just doing homework, going through your notes, that kind of stuff. That's awesome. That's a great experience. Most people don't have that situation, but that's kind of the ideal, at least.
I found that physics took more like 40 plus hours a week for you to actually understand it.
Really?
Yeah, that's kind of how my first one was. The second one was really taking a lot of time, so I plan on going to UW, so I don't need the second or third one.
Oh, okay.
So hopefully I get in there. Otherwise, I'm doing summer physics at PCC.
There you go. Yeah. And summer of physics is not a bad way to spend your summer if you can do it. I think it would be kind of life-changing in some ways, You might come out and be a physicist.
I feel like I wish I would have known that last summer. I would have just done it.
Yeah. So for those who don't know, there's this option, we kind of informally call it Summer of Physics. It's at Portland State University, and they offer in the summertime the equivalent of all 3 of the physics classes at Clark, and you can get through the entire year of physics sequences in one summer at PSU. But it's the only thing you're doing. I mean, it's about 6 hours a day, 5 days a week. And, the first class ends on a Friday. The second class begins the following Monday. And that's the whole summer. It's just intense, immersive physics experience. And, again, if it's an option time-wise and lifestyle-wise, it might be a really cool way to just sort of immerse yourself in this, get through it and not have to juggle it with other stuff. But you know, most people can't afford to just spend the summer doing classes. But I've had some students who do it, and if they survive it, it seems like it's been a good experience. If, yeah, when. All right. Any questions on? We were finishing up cues, and I don't know if I finished talking about the tail pointer or not. I think I still need to talk about that. But mostly we finished up stacks and cues on Tuesday. But any questions up to here?
I have a question on PA2 just with parsing. Do you want me to wait till later?
Yeah, because I'm going to do PA2 after we wrap up whatever we have to wrap up.
Okay. Yeah, I'll go ahead and wait then.
Okay. So let me just talk about tail pointers for cues. So remember, a cue is a first in, first out. And so typically, our cue would look something like this. And we're going to, you know, add to one end and remove from the other end so that this stays in order. If we add and remove from the same end, it's a LIFO, it's a stack. But for a cue, where we want to do things in the same order, we want to take things out in the same order that we put them in, we're going to have a linked list and just add to one end, remove from the other. And at some level, it doesn't matter which end you add to and which end you remove from, but for efficiency, it turns out things work a little better if you add things at the end of the cue. So we make this the tail, and we make this the head. All right, why is that helpful efficiency-wise? Well, whatever you do at this end of the list is order one, right? Whether you're inserting or removing, all you have to do is start from the sentinel and either, you know, insert a node right at the beginning or remove that first node. That's order one. So whatever we do at this end, whether it's the add or remove, will be order one. But whatever we do at this end, the tail end, we need to get to the tail first. And one way to get to the tail, and this is the way I suggest you do it in PA2, is just start from the head and just move down the list until you get to a node that's pointing to null. And when you get there, you know that that node is the last node. And then if you want to add something after that, you just, you know, add a new node and point to it. But the advantage of putting the tail down here is that you might be able to make another variable called a tail pointer that keeps track of where the end of the list is. And now if I want to add something else, like when I'm adding to my queue, if I want to add something to the end of the list, I don't have to start at the sentinel and move down. I can just follow my tail pointer, and it'll take me right there to the last node. I make my new node, I have the tail pointer point to it, and now I've effectively moved my tail. And this is still order one, because no matter how many nodes I have in my list, it's a fixed set of operations to add something to the tail. Follow the tail pointer, make a new node, have that last node point to the new node, update tail pointer to point to the new node, and you're done.
So the tail pointer is pointing to the address of the last node.
The tail pointer is the address of the last node, yeah, so it points to the last node.
Okay.
So could you make tail pointer equal to null's data or null?
Say it again?
Could you make the tail pointer equal to null or null's data? Or do you have to jump through the process and say that it's going to skip down the line until it hits the end?
So the idea is you always keep tail pointer pointing at the tail. And if you add something else here, you change tail pointer to point to that new end. And so it's always pointing to the tail, right? So you never have to search for where the list ends. You've always got something that's referring to the end of the list. Your alternative...
Current,
Go ahead.
current next is equal to null, and then tail pointer is equal to current, kind of a thing.
Well, so what would it look like to add something? So, you know, new equals malloc. So make yourself a new node. As usual, store the number n in there. And then tail pointer next would just be set equal to new. So new equals malloc. Here's your new node. You store an n in there. Tail pointer next equals new. Well, tail pointer right now is the address of this last node. So tail pointer arrow next says go to that address, pick out the next field, right, and have that equal to the address of n. That makes this last node point to n. And then tail pointer equals new. That changes tail pointer to point to this. And, you know, as usual, have your new node point to null to say it's the end of the list. And so, you know, fixed set of operations let you pop something else on the end of the queue, regardless of how much stuff you have in the queue. So that's where we're getting this order 1. The trick to doing this is you need to have somewhere to store the tail pointer. So in the past, I've let people define a separate node structure for their queue, and they could put a tail pointer in there. But for PA2, I'm forcing you to use the exact same node structure for queues and for stacks that you used for linked lists in PA1. So it's pretty tricky to get a tail pointer to work, but you can take it as a challenge if you like. But theoretically, this is how tail pointers work. And they only work if you put the tail down here. They don't work if you put the head down here and the tail at the beginning. Because if the head is over here, what do you do at the head of the queue? You remove. And so I can get to the node I want to remove really quickly, but to remove that, I need to know what the previous node is so I can change it to point to null. And so a tail pointer won't help me do that. In other words, I have to back up. And unless I have, you know, a doubly linked list where nodes are pointing forward and backward, the tail pointer doesn't help me once I delete that last node. But if I make the tail back here where I'm adding, right, to add something after this, all I need to know is the address of this node. So tail pointer works great there.
So this would be kind of a challenge for this one.
Yeah, and I thought of a way to do it this morning. And it's pretty sneaky.
I suspect you won't share that with us.
I won't. And I won't give points for it because then the calculus changes. But if you want to figure this out, I've decided this would be an excellent interview question. And it actually led to another interview question that I thought of. So yeah, it might be a fun one to work on. When you're done, you know, with PA2 and you're done with physics and you got, you know, spare cycles, could be fun to think about. All right. Any questions on any of that? Stacks, queues, implementation with lists, incrementation with arrays. What that bright object is behind me. All right, well, let's go on and talk about PA2. So this is your second programming assignment. I posted this on Tuesday night. And this is due a week from tomorrow. So, PA2, you're going to implement stacks and queues using linked lists. So not using the funny thing we did with arrays with a stack pointer and circular arrays and all of that. We're going to use linked lists. And you can actually reuse a good chunk of code from PA1 if you got your linked list working in PA1 for the lists you need in PA2. And a lot of the requirements on the lists are identical to what they were in PA1. The structure of the node, the cleanup function, and so on. You're going to implement stacks and queues using linked lists. You're also going to implement a main program, again, that lets the user interact with your lists and queues through a set of simple commands. So same basic framework as PA1. So you'll develop two things: package of function calls for implementing those data structures, and then a main program. So a note up front here, right? Your program for PA1 worked with a linked list. You had one linked list, and so if you inserted a number, you knew where it went. If you wanted to print the list, you knew what to print. In PA2, you're going to have two separate independent data structures sitting inside your code. You're going to have a stack and you're going to have a queue. And they're basically completely independent of each other. So when you execute a command from the user, like, print, you need to know, should I be printing the stack or should I be printing the queue? When the user says, add the number 17 to my data structure, you need to know, am I adding it to their stack or am I adding it to my queue? And rather than have different commands for add to a stack, add to a queue, this program has a notion of state. So the program is always in one of two states, stack mode or queue mode. And all of these commands that your program can respond to, what they do depends on what mode the program's in. So the program begins in stack mode. And you can switch between stack mode and queue mode by using the commands S and Q. And the main things you do are you put things into your data structure, you take things out of your data structure. Alright, so how do you add a number to your data structure? You just type an integer and hit enter. So there's no special add command or insert command. If I just type 12 and hit enter, I'm asking the program to put a 12 either onto my stack or onto my queue. Which one depends what mode I'm in. So if I start off in stack mode and I type a 12, it should push a 12 onto my stack. If I type a 15, it should push a 15 onto my stack. Anytime I hit enter with nothing else on the command line, I'm trying to remove something from my structure. So if I'm in stack mode, that would print out the 15 and remove it from the stack. If I hit enter again, it would pop off the 12, remove it from the stack, print that out. If you're in queue mode, exactly the same thing, except these things are being added to and removed from a queue instead of a stack. And then you can switch between the modes by doing S and Q. So S puts you into stack mode, Q puts you into queue mode. These commands also print the current contents of the stack or the queue. And if you're already in queue mode and you want to see the contents of the queue, just hit a Q. You're already in queue mode, so changing into queue mode doesn't do anything, but it will always print out the contents of the queue. And if you're in stack mode and you hit an S, all it does is print the contents of the stack. And then X exits the program after cleaning up all of the memory as usual. Anything else should give you a help message. All right. And then don't print any additional output messages. If you pop something from the stack and now the stack's empty, don't say, hey, now the stack is empty, right? If you insert something, don't say, hey, I inserted the number 5 for you, right? Very, very minimal output, just what's specified in the assignment prompt. And so you do need to keep track of the state of your program. That's just going to be a variable. You can have a mode variable that can be equal to, 1 if you're in stack mode, 2 if you're in queue mode, or whatever you like. All right. So before we go into implementation details, let me show you what this looks like as a sample executable. So on the Linux server under /temp pa2 sample shows you a sample executable. This is what your program should do. Very, very, very minor differences are okay. You don't have to print a usage message in the beginning. It's up to you. You don't have to make your usage message look like this, but somehow tell the user what their options are. You don't have to print a welcome message, but it's nice to be friendly, right? But the behavior of these commands has to be pretty precisely what you're seeing here. So I'm starting off in stack mode, and I can, do a 10 and a 20 and a 30 and a 40. Those should be getting pushed onto my stack, right? And it's not telling me anything. It's just silently pushing those on the stack, so I don't want to see a lot of extra output here. But if I want to see what the stack looks like, I can use the S command. It says switching to stack mode, and then it shows me the contents of the stack. And this output has to be precise, and I spell this out in the assignment. I want to see top of stack, dash dash greater than, like a little arrow, and then the contents of the stack on one line separated by spaces. Let me bring this up off the bottom. All right, I can put a 50 on, and now if I look at my stack, it's got a 50 on the top of the stack. And it's this last in, first out behavior. The last thing that I push on the stack, that's what's sitting at the top. That's the first thing that's going to get popped. All right, how do you pop? Just hit an enter. So there's my 50. If I want to pop again, hit the enter again, there's a 40. And if I look at my stack now, it's a 30, 20, 10. I can pop off the 30 and the 20 and the 10, and if I look at my stack right now, it's empty. If I try to pop from an empty stack, that's an error. Tell me that's an error. The stack is empty. I can put some stuff back on the stack. Now I got 5 things on the stack. It's a stack, so duplicates are fine. We're not keeping this in sorted order. Right? We're just pushing things in, and then we're going to pop them off in the opposite order of how they were pushed. So everybody good on stack behavior? So if I want to look at my queue, I type a queue, that puts me into queue mode. And it shows me my queue, and there's, you know, the head on the left and the tail on the right. It's got to be like that, and there's nothing in my queue. So I can put some...
If you switch back to stack, is it going to be the same stack?
If I go back to stack, my stack is still there. It's unharmed. If I go back to queue, there's the queue. I put in a 2, 4, 1, 3, 5. So the head of the queue is a 2, 4, 1, 3, 5. 5 is the last thing I put in. If I want to remove what's at the head of the queue, just hit an enter. There's my 2. There's the remaining queue. I can go back to stack mode. There's my stack. If I want to pop off that funny number at the top, I just hit enter. And that's what my stack looks like now. Again, with a queue, you know, there's nothing magic. It's just storing integers in this first in, first out structure. Always with the property that the first thing that I pushed is going to be the next thing that I remove. So I just pushed in a 3, that's going to be the last thing that comes out. But this 4 up here that's about to be popped off, that's what I put in up here. When I first, you know, went from an empty queue, I added a 2 and then I added a 4. That 4 is going to be removed. If I hit an enter, it removes the 4. And then the 1, the 3, and the 5. That's the whole program. Alright, 2 data structures, a stack and a queue, both existing at the same time, independent of each other. And I can interact with those structures through these simple commands. Type a number, it adds it to the structure. Hit an enter, remove one thing from the structure. And then change mode and print the structure using S for stack mode or Q for queue mode. And just like with the stack, you know, right now I've got 3 things in the queue, 1, 2, 3, so I can remove the 1, 2, and the 3, my queue is empty again. If I try to remove from an empty queue, that's an error. Go ahead and say the queue is empty, and that's an error. But my stack is still intact. And then when you're all done, anything odd should, you know, give you a help message. And when you're done, you can hit an X, and that should clean up all the memory and then take you out.
And so the error message, that's going to be in our main function, right?
That's going to be in your main function, yeah.
Okay. Or main program, excuse me.
Main program, yeah. It is a function, actually. So you can say main function. Alright, so details. Implement the stack using a linked list. Implement the queue using a second linked list. So you have 2 sentinel nodes pointing to 2 different linked lists. So your main program is going to call a init twice. Once to get a linked list for the stack, once to get a linked list for the queue. And it's going to have 2 of these pointers inside your main program that it will use, you know, when you want to add to the queue. It'll use the queue sentinel node pointer and pass that to the appropriate function. Alright, for the stack, push elements by adding immediately after the sentinel, pop from immediately after the sentinel. So do your stuff right at the beginning. For a queue, remove from the head as usual, add to the tail. The head is right after the sentinel. So you remove from the node right after the sentinel, just like popping, but you add by putting things in at the far end after the last node on the list. Alright, special notes. You should not run out of memory. I'm not going to try to make you run out of memory, so I'm not worried about whether you check to see if you're out of memory or not, because we don't always have a way to return that information. If the user tries to remove an item from an empty structure, either a stack or a queue, your main program should print an error message, right? But don't throw the user out, don't exit the program, don't segfault, don't corrupt the memory, don't zero out the stack or queue, right? It's just a user error. Don't make the poor data structure pay for the user's bad behavior. So it's just, you know, print a message and life goes on. Keep your structures intact. If they try to pop from an empty stack 10 times, just print an error message each time. But then if they turn around and try to add something to the stack, that should work fine. And nothing you do on the stack should affect the queue or vice versa. Alright, moving between stack and queue mode should not affect the contents of these data structures. Alright, required structure. So you've got to use a struct mynode. It has to look exactly like this. Integer data and then a struct mynode star next node. And nobody got tripped up on this, but just to be clear, right, this has to be defined in this order. If I were to define my struct mynode pointer first and then my integer data, all heck breaks loose. So the order in which you define the pieces of a structure is significant. So use exactly the same mynode structure that you used for PA1. And then you have to implement 11 functions. Oh boy, 11 functions, that's a big number, right? It's really not a big deal, okay? You got to do these 11 functions to implement your stack and queue, but some of these you've already done. Some of these are going to be the same as others that you're going to do, and so on. So stack init initializes an empty linked list corresponding to a new stack. Hey, that's your init function from PA1. There's no difference. And by the way, queue init is going to be exactly the same thing. So all you got to do is take your init code and make 2 copies of it and call one of them stack init and call one of them queue init, and you're done with those 2 functions. But, you know, put some comments in the top and say, this function that I spent, you know, 5 years creating is for initializing a stack, you know, and get some credit for it. But it's really the same code from init from PA1. So those are done. Stack push. So this is easier than your add function, but this is, you know, the simplified add function that we worked through when we were first talking about PA1. It adds right after the sentinel node. So, you know, new node equals malloc, new node number equals whatever number you want, new node next equals sentinel next equals new node. That's really all there is to it. So push is not bad. And then pop is also a subset of delete. You don't need to search for the node you're going to delete. You're just deleting the first node right after the sentinel. So what does that look like? So remember what the sentinel's pointing to right now, right? And save that as free this, and then set sentinel next equal to whatever that node you're deleting is pointing to, and then free what was the first node. And that deletes the first entry in a list. So if this is what my list looks like, free this would be this first node right here. Sentinel next equals free node next. Well, free this is pointing here, so Sentinel will point over here. And then when I free this, this goes back into the heap. And what can go wrong here? What's the error condition?
If you order it wrong and delete the node first, you won't have anywhere to put the next one.
That's true. If I free the node first, I've got a problem. What's the other error condition though, even with the code written like this?
If it's the last node, right?
Yeah. So if there's only well, if there's one node, if my list looks like this should work fine, because this will be free this. Sentinel next will be what this is pointing to. Well, that will make the Sentinel point to null, which basically makes the Sentinel the last thing in the list, and then releases that. So that'll turn a list with one thing to a list with 0 things. But yeah, as someone just said in chat, if the list is empty to begin with, if my list is just this, then free this will be what the Sentinel's pointing to, that's null. And when I try to see what that's pointing to, that's going to segfault. So right here, if free this is null, that's an underflow. So at that point, I would want to do something in response to there being an underflow. But what I'll tell you in this PA2 write-up, though, is you don't have to catch this error. But you don't want to segfault. So if free this is null, just return. But I'm not going to ever call your remove or pop functions with an empty data structure. So I won't exercise that case. But if you want, right, just return silently. Alright, so that's what a pop is. Is empty. How do you tell if a stack is empty? What would be your one line of C code?
You just check Sentinel next, right? And make
Just-
sure that's equal to null.
Yep, check Sentinel next. So Sentinel will never point to null. Sentinel is guaranteed once you set it equal to the return from a init. Sentinel is pointing to something. But Sentinel next could be null. If it is, your structure is empty.
So that's probably the easiest function here.
That's the easiest one to make, yeah. And guess what? Stack is empty, queue is empty, exactly the same code. So that's bonus. And then stack print, that's your print program from PA1. The only difference is at the left you've got to say TOS -- greater than. But since the top of the stack is at the node right after the Sentinel, if you use your print routine from PA1, which prints from the Sentinel on down, right, it's going to print out exactly the right thing. So init is done. Push is the simplified add function. Pop is you know, this thing. Is empty is a one-liner. And print is the print from PA1. And then for the queue init's the same init that you used for stack init is the same init you used for PA1. Add is exactly the same as pop, right? So you're going to get a lot of practice with, you know, taking a set of code and wrapping it differently and adding a different, you know, comment block in the beginning. That's going to be a lot of your work around writing these functions compared to, you know, digging into 50 lines of pointers and mallocs and all that kind of stuff. Alright, QRemove is the one kind of new function. So this is still a subset of delete, but instead of looking for the spot where you should delete, you're simply looking for the last node and then removing that. And so how do you find the last node of the list? So normally we do temp equals sentinel next. And then while temp is not equal to null, we do temp equals temp next. And when we're done, right, we're exiting because temp is equal to null. That's our standard loop for printing, for searching, all that kind of stuff. The problem here is that when this loop finishes, temp is not pointing to the last node, it's pointing to null. That's how we got out of this. So if you use your previous current structure, right, when you get to the end and your current node is null, previous will point to your last node. There's a different way you can wire this up though. And this is a really good practice to think about. And see if you can reproduce this code without looking at it, right? See if you can figure it out based on its behavior. So if we start with temp equals sentinel, and we go until temp next is null. Okay, so here's temp. Temp next is not null. Change temp to here. Change temp to here. Temp next is not null. Change temp to here. But at this point, temp next will be null. We'll exit the loop. And now temp is the last node. And if you started with an empty list with just a sentinel, this will set temp equal to the sentinel, while temp next is not null. Well, if this is an empty list, sentinel next is null, we'll kick out of our loop. And again, temp is the last node, in this case the sentinel. Or rather, it's the thing right before where you want to add your new node. And so if we don't have a tail pointer, right, we do this, and after we come out of this loop, this is your tail pointer. This is telling you where the last node is. So now it's just temp next equals new node.
This would be for the add, right?
This is for adding to the tail of the queue.
Okay.
Yeah.
So we're talking about queue remove, so that.
Oh no, this is for queue add.
Okay.
Yeah, sorry, I got those backwards. This is for queue add. Queue remove is exactly like the pop, because you're removing from the node right after the sentinel. So queue remove is pop. Queue add is this funny one that goes down to the tail. And then is empty looks exactly like the is empty for the stack. And queue print is exactly like your print from PA1, except before you start printing, print out head with an arrow, then do your loop from your print function for PA1, and then do an arrow and the word tail. And again, if you're putting the head right after the sentinel, your print function will print these out in the correct order.
Can we put the code for the queues and stacks in separate scripts? Is that outlined somewhere?
It's all got to go in one file called functions.c.
Okay, I guess I would just separate them by comments.
Yeah. All right, and then you have a cleanup function, and that just calls your cleanup code from PA1. And the user calls this with either, the pointer to the stack or the pointer to the queue. So your main program will want to call cleanup twice. Once to clean up the stack and once to clean up the queue.
And that one, it doesn't matter what order it goes in ultimately, it's just going to clean it up from end to end, right?
Just cleaning up from end to end, but it's pretty straightforward to clean it up starting from the sentinel. Like we did in PA1. It's pretty hard to do it any other way.
Well, no, meaning like we're going to call it twice, but we're going to call it for each list. But it doesn't matter if it starts from the beginning or the end. It doesn't matter if the list is a queue or a stack. It's going to start from the sentinel and work its way down no matter what structure. Okay.
Exactly. Yeah, your cleanup's just going to see a linked list. It's not going to really care how you're treating it.
Okay.
And that's a cool point to keep in mind, right? This is really just a linked list. Right? There's nothing inherently stacky or queuey about the struct my node or about the way that these things are pointing from one to another. The only thing that's making a list is how your code is using. The only thing that makes it a queue is how your code is using this list. The only thing that makes it a stack is how your code is using this list. So underneath, you know, it's just a bunch of pointers pointing from one to another. It's a chain of struct my nodes. All right, so errors. Your main program should report errors for popping from an empty stack, removing from an empty queue, or any syntax errors in the user's command. If they type a command that's not recognized, right, that's an error. If they go blah blah blah, that's an error. If they try to insert 23.2, that's an error. If they just hit an enter, it's a pop, so that's not a syntax error. But so popping from an empty stack, removing from an empty queue, or any syntax errors in the user's command. So those are the errors that you want to catch and print a message for. Your functions do not need to check for popping from an empty stack or removing from an empty queue. This error checking is the responsibility of the calling program. You also do not need to check for running out of memory. So when you add something to the queue or you push something to the stack, you don't need to see if you're running out of memory. And so these add functions and the push function, I'm setting those up to just be void. So if you run out of memory, again, don't segfault, just return. Alright, program structure, same as PA1. Main.c is your main program and any functions you write that support the main program. Functions.c is the linked lists, is the stack code, the queue code, and any other functions you write that support that code. So it's going to at least have those 11 functions from above. And then anything that you're going to do, you know, any functions that you're going to call from there that you're writing should also go in functions.c. So functions.c is your stack and queue package. And when I do my test with my own main program, I'm going to link my main program to your functions.c. And it should, you know, everything should work. So there shouldn't be anything magic in your main program that's being used, you know, internally, like global, you know, variables or things like that. Everything in this description of your stack and code also allows you to have multiple stacks and multiple queues. So if I call stackInit 3 times and I save each of those return values in a separate variable, I should have 3 stacks. And I could push into my first stack by passing it, and I could push into my third stack by pushing that here, and so on. So no globals. Alright, main.h should have your structure definition, your struct my node, and it should have function prototypes for all the stuff in functions that the main program is going to call, so mainly those 11 functions. And then the usual well-written make file that produces an executable named main out of main.c, and should include a clean target that removes main.o, functions.o, and the main executable.
And real quick, when we were talking about make files the other day, you were saying not to put the header in a certain section because then it creates like a GCH file or something like that.
Yeah.
Where was that at?
So you don't want to you don't want a GCC and H file. So for example,
okay. So you put it in your target, but you don't GCC it.
yeah. So let's. So here's my make file from PA1. So main.o is built using main.c. That's one of the dependencies. It also requires main.h. Right? And that's important, so that if I change main.h, this will get recompiled. But the error is if you put main.h there. And then I do a make. I've now got this main.h.gch. Because this is what you're asking the make file to do. You're asking it to compile main.h and create an object file. Well, there's no code generated by main.h. right? So there's no object file possible. This doesn't generate code. These don't generate code, right? This is just defining, you know, what a structure is and so on. And so you get this weird main dot h dot gch that's just, you know, weird stuff. But 1600 lines of weird stuff. That's kind of cool. I saw finite math only up here. Ooh, and I saw atomic character lock free. That's a good band name. All right, any other questions on the makefile? All right, your choice how much, if any, code you reuse from PA1. If you want to take code verbatim from there and reuse it, that is not plagiarism because it's your code. So you're totally allowed to do that. And like I say, a lot of what you're writing for PA2 is the same linked list stuff. So feel free to repurpose your code. But, you know, some of it you're going to have to change. And I don't, you know, suggest necessarily trying to force your delete function to act like a pop function, right? Rewrite your own, you know, pop function, but you can use what you did for delete as a template maybe, you know, or to remind you how to touch up a node to skip over a node or when to free it or something like that. So, your choice. Sample program, sample executable on the server, temp PA2 sample. You can use that to see what the code should do, what your main program should act like. Okay. But, you know, important note, even if your program acts exactly like that sample code, right, you could get a 0 on it. So if you're not breaking your functions up the way that I've specified, if you're not naming things the way I specified and so on, there's still a point loss possible. So this is a necessary, but not necessarily sufficient condition that your program acts exactly like the sample code. All right, deliverables, tar file named pa2.tar containing exactly 4 things: main.c, main.h, functions.c, and makefile. There's a handy-dandy tar command you can use to create that archive. Be careful with this. Again, if you forget to type this part of the command, you will clobber main.c. It will be gone. There's no going back, right? Unless you have backups, which you should. But so be careful with this, right? And maybe copy all your files into a work area and do your tar file creation in there. But also, you know, have backups. Make copies in other directories or external drives or Dropbox or something. Or, you know, maybe Git. All right, and then upload pa2.tar to Canvas by the deadline. Strongly encourage you, after you've got a tar file that's ready to go, copy it to an empty directory, untar it, and you can untar with this command, tar xvf pa2.tar. And this will extract all the files in here and drop them into your current directory. Do this in an empty directory. It will overwrite whatever's in the current directory. So if something goes wrong and you're in the directory that contains your only copy of your functions.c, you might wipe out functions.c. So do all of these things in like separate directories, right? You should be getting comfortable with moving around directories, creating directories, copying files, and things like that. So move into a new directory, untar in there, execute the make command, and then run your test codes and make sure it still works. All right, your submission should include complete implementation of the linked list-based stacks and queues, a main program as described above, plenty of commenting, specifically for each function, right? Block of comments before the code that describes the function name, the set of arguments, what those arguments do, what the return value is, what the return value means, any assumptions, any odd side effects, anything that you want to note. Okay, so 11 functions, right? That's a lot of documenting. The code, the writing of the code is the smaller part of this project, right? if you understand PA1, it might take you, half an hour to actually write the code. Other than main, main's a little more challenging. But the functions themselves, probably won't take you that long. But putting it in the right format, documenting everything, writing the main program, testing it, all of that stuff is going to be where you spend a lot of your time. So good comment blocks before each of those 11 functions. Those functions are the user's interface to your code. So you definitely want to spend some time, explaining those. Additionally, your code should be commented throughout. Anything that's not absolutely perfectly clear why it's happening, put a comment in and say why it's happening. And then comment block in the beginning of the main program with your name, class, date, assignment number, and synopsis in your own words of what the program does. And then a make file that builds the executable named main and includes a clean option. Alright, grading straightforward, it's pretty similar to PA1, so no submission, corrupted tar file, etc., no points. Compile errors that stop me from running your code, you lose 50% up front. And then if I can pretty easily get your code to run, I'll do that, and I'll continue testing your functions and so on. If you don't name things correctly, don't use the struct node, don't follow exactly the function names, don't have the same prototypes, and so on, that's 50% off. And if you don't split it into those 4 pieces with all of your stack and queue stuff in one file and so on, that's 35% off. If you decide to implement this using arrays instead of linked lists, or magic fairy dust instead of linked lists or something, that's 100% deduction. So it's got to be done using lists. And then
Comment block with our name and everything should only be in the main program.
That's just in main.c. Yeah, I don't mind if you want to put that in functions.c, and personally I would do that, something like that also, because it's my code, I want my name in there, but I've got to see it in main.c.
Okay.
Cool. Alright, and then you get points for the following: makefile 5%, push and pop 7% each, add and remove 7% each. Correctly managing state, being able to switch between stack mode and queue mode, that's 10 points. Correctly printing the stack and queue contents following the S or Q command, that's 20 points. This is code you've already written. All you got to do is make sure you add the proper header in the front, right? So when you print the stack, TOS -- greater than, print the stack. When you print the queue, head -- greater than, print out the numbers less than -- tail. So that's 20 points. Main program, 10%. And that's all or nothing, right? So that's got to handle syntax errors. It's got to handle, things that aren't integers. It's got to call things correctly and so on and so forth. No compile warnings when you compile with the default GCC command, 5%. And then your 4 types of commenting and indenting, 3% each, same as before. All right, questions about that so far? So I'm planning to talk about the main program next, but there was a question in the beginning of class about parsing. This would be a good time to ask it if you like.
Yeah, mainly it was setting up the scanf to detect an enter, and then also, doing just an integer.
Okay, cool. Yeah, so we're going to talk about that next. How to do that and how to tell if somebody entered an integer and so on and so forth. So let's take a break first, because that was a long segment of discussion with lots of energy. So let's take like a, I don't know, 6 or 7 minute break, and we'll come back a little after 2, and we'll talk about how to think about your main program for parsing integers and commands and so on. So let's go down to let's go for 5.5 minutes, and I'll see you back here then. Alright, welcome back. Alright, so let's think a little bit about the main program. Because the command structure is kind of quirky, right? You have 3 commands that you can specify by just typing a letter, and they're single letter commands, SQ and X. And you also have an implicit command that you get by just typing an integer with no particular character in front of it. And then you have an implicit command that you get by just hitting enter. And these are all sort of different cases. So let's do some sample code. So let's just do a simple infinite loop, and let's do an fgets. We'll print a prompt and we'll read a line of input from the user, and let's look at parsing it. So let's print out buffer bracket 0 first. It's going to be a character. And I'm going to delimit my %c with angle brackets so I can see very clearly what that character is. And that's my whole program. I'm just going to play with fgets and looking at the first character of the buffer that I ingest. And so if I say hello, the first character is H. If I say S, the first character is S. If I say space, the first character is a space. If I say enter, the first character is, well, it printed my opening delimiter, and then my closing delimiter appeared on a new line. So we have good reason to suspect that maybe the value of buffer bracket 0 is a new line. And in fact, that's what it is. So if you look at the man page for fgets, fgets reads at most 1 less than size characters from the stream, stores them into the buffer, reading stops after ERF or new line. If a new line is read, it is stored into the buffer. So this is this business from last quarter where we noticed that every time we input a string, if you say hello, the string actually contains 6 characters, HELLO, followed by a new line. Well, we can use that to our advantage here. And I'm just going to look at if bracket 0, buffer bracket 0 is equal to, I'm going to do single quote \n because I'm looking for a single character. Right? If I do double quotes, that would be the address of a string that contains a new line followed by a null. That's not what I want. I just want the single character \n, which by the way is ASCII code 10, right? It's just an 8-byte value. So if buffer 0 equals that, let's print out a message and say you hit enter. So 2, 3, hello, but if I just hit enter, it says you hit enter. So that's one way we can pick that up. All right, the other question is, you know, if the person types a number, we don't recognize that, right? The first character is just whatever the first digit is that they wrote. So this is where we want to use scanf. And anytime you're trying to tell if the person typed in an integer or if a string contains an integer, go to scanf, right? It's going to do all the hard work for you. So, is this an integer? Well, we're looking for an integer right at the beginning of the line, and we don't want anything extra coming after that integer. So I'm going to scan with a %d, %s, the usual trick. Put the first thing into num, put the second thing into just this extra holding buffer called extra. Alright, if the person typed exactly one integer, what should my value from the call to scanf be? What's the right value to check for here?
Should be just one, right?
Should just be one. I was going to give you 5 guesses. You got it on the first try. So if scan result is 1, that 1 means that the scan matched one thing. It converted one thing using this pattern, and it saved one thing over here. Well, since the first thing we're asking for is a %d, returning 1 means that's all it matched. It found an integer. It did not find anything that matched a %s, which would have been anything after the %d. So if scan result equals 1, it matched one thing, which is the %d. That's good. And let's just print a message to tell the user, hey, you entered an integer, and let's tell them what the integer is. So, you know, this stuff comes out normal. If you just hit an enter, it says you hit enter. But if you type in a number, it should say you typed in an integer. And if you type something that's not an integer, it shouldn't tell you that you had an integer. All right, how do we put all of that together? So, print a prompt, read the input, check to see if this is an integer. So use your scanf, see if the return value is 1. If yes, you know, add or push, and go back up to the top of your loop. If it's not an integer, well, it should either be an S, a Q, an X, or a new line. And so this is a nice place to use a switch statement, or you can do, you know, 4 if statements. But switch works well when you want to compare something small, an integer, a character, a short int, things like that. So we could just switch on buffer 0. If it's case S, do what we want to do. If it's case Q, do what we want to do. If it's case \n, that means they just hit an enter, so do your pop or your remove. If it's a case X, call cleanup twice, say goodbye and exit. And then you can say default. And default is where you print out a help message. And then go back up to the top. And probably after each of these, go back up to the top. How do you go back up to the top? Well, you got a few options. One way is to say continue. And continue will take you up to the top of your current loop. But the other way is, you know, put a break statement after each of these to take you out of the switch statement, and then just have the bottom of your loop down here. And up here, you know, you could either do a continue to go back up to the top, or you could say, you know, if this is an integer, then do this. Otherwise, and do this switch statement, right? The downside to that is now your switch statement is indented, you know, extra spaces, because it's all inside the else statement of this if statement, way up in the beginning of your loop, which is all wrapped inside a loop. If you can avoid getting too deeply nested, your life gets a little easier. The debugging gets a little simpler, the kind of silly mistakes become fewer. And so, you know, anytime I can get out of something rather than just you know, putting it inside another level of logic, I'll try to do that. Yeah, X is an exit, so you know, return, clear your memory, say goodbye, and then exit the program. Just say return if this is your main program. if you take all of this and you throw it inside a separate program, a separate function, like I did in my sample code for PA1, right? Getting out of here is just a matter of returning, and that can be useful too. But however you wrap it, right? That's just, you know, decisions as a programmer. But that's basically what the parsing looks like. So most of these commands you can pick up by just looking at character 0 of buffer. Integer, use scanf, and you know, remember that you know, anything that I type that begins with an S, buffer bracket 0 is going to be an S. So the way I'm describing this, S would not only would S put me in stack mode, but anything beginning with an S would put me in stack mode. Is that a problem? Right? Apparently not. So this is where you can use a sample code, right? The sample code does not report QQQQQ as an error. It just picks up that first letter Q and says, oh, you want to go into Q mode. Okay, that's fine. So you're allowed to do that too.
If you put S or Q followed by an integer, it won't matter. It'll just look at that first character.
Yep.
Okay.
So simplifying assumptions, right? I'm not putting all of this in the assignment, because then the assignment would be, you know, like 80 pages. But, you know, go to the sample code, and if there's something really, really wacky going on in the sample code, go ahead and ask, right? Like, hey, did you mean for this to delete all my files when I insert a 12? But, you know, generally, if this does something, you're allowed to do it too, right? This is the gold standard. It won't delete your
What were we
files.
talking about in the last one? When I hit make clean on the sample, it just
Right, right. Yeah, so secret backdoors, you know, insert this combination of numbers and suddenly it, like, you know, gives you root privileges or something. That's another class. All right.
I think you just enjoy that, though.
Yeah, yeah. Of course, I've never done anything like that personally. No.
Yeah, of course.
Of course. All right. So any questions about that?
I'm reading through the document here. Is there anything you want us to set the Sentinel nose data to, like in the last one?
Nope, not required.
Okay.
But set it to, if you're ever going to look at those data values, make sure you set them to something. Otherwise, I think Valgrind will give you warnings.
Fair enough.
So, and it's always nice to set them to something.
Probably just leave it verbatim the same.
Yeah. All right, last detail for this. Let's talk about stateful behavior. Let's not talk about direct proofs or chain rules. Let's talk about the stateful behavior of this program. So, you know, you say S and you're in stack mode. You say Q, you're in Q mode. The funny thing about this is, you know, if I type enter, so, you know, buffer bracket 0 is a new line. And let's just suppose I'm doing an if instead of a switch. Well, I might want to do one of two different things. I might want to pop from a stack, or I might want to remove from a queue. Now, you know, somewhere in the beginning, I said, you know, struct my node star stack equals stack init. So I do that somewhere in my main program, and I also say struct my node star q equals q init. You can call these whatever you want, but somewhere, you know, before my main loop starts, I'm going to call stack init and q init. Those are going to give me sentinel nodes for my stack and queue. I'm going to save those. And so in here, you know, what I want to do is either stack pop. Let me make sure I'm using the right function names. So I'm either going to call, you know, stack pop, and I'm going to pass the sentinel node to the stack, or I'm going to say, you know, x equals q remove from my queue, and then I'm going to print x and whatever else. But which one of these am I going to do? It depends what mode I'm in. It's the same input command, it's the same if condition that's testing as true, but I might do something different. So I'm going to need a state variable. Somewhere in the beginning of my main program I'm going to have, it can just be an int, which I can call mode. And maybe I'll initialize that to 1. And I'll put a flag here which says, you know, 1 equals stack, 2 equals q. That's going to tell me what mode my program's in at any point in time. And so if the person types enter, and I detect that because buffer is just a new line, I'm going to say something like, you know, if mode is equal to 1, then let's pop the stack. And I could do an else, or I could make another if mode equals 2, what I'm going to do is remove from the queue. And so depending on the mode of the program, I'll either do a pop or I'll do a remove from the stack or the queue. But I'll save those in X, and then either way I'll go ahead and print X. And then how do you move from mode to mode? Well, you know, if the command that the person typed in is an S, then maybe I'll do something like mode equals 1, maybe print a message saying you're in stack mode, and then call stack print and pass it the sentinel node to my stack. And if the person types the command Q for Q mode, right, I'll set mode equal to 2. I'll print a message saying you're in Q mode, and I'll call Q print and pass it my Q. So this is stateful behavior. And it's a really, really powerful concept. So engineering 250, we talk about state machines. And you know, we store the state in a bunch of flip-flops. Well, we can use the same concept in software. Instead of a flip-flop, you know, we've got a handy-dandy integer, which is actually like 32 flip-flops, right? But we're using a single bit to store what state we're in. And then, you know, with a state machine, you have fixed hardware, but it does different things depending on the state. Well, here we have fixed code, but it does different things depending on the state. And it's a really, really kind of powerful way to think about implementing algorithms. So the additional textbook on Canvas, the one called I Can See Clearly Now, that has a chapter on stateful programming. If you want to think more about this or read more about it, there's a few pages in there that talk about this and some examples and exercises and so on. So you can definitely use that here. And it's a really powerful concept. If you haven't done Engineering 270 yet, this will help you when you get to 270. Because there's some labs in there where you have to do exactly this. You have to respond to state. All right, the other thing I'll just mention. Go ahead.
Can't wait till we get to OO.
Yeah.
It gets a little bit easier.
Yep. All right, the other thing I'll mention here is using defines. So C has this, you know, number sign define that lets you basically set up a symbol. So you can pound define and make something a symbol for something else. And that's a fairly useful thing to do here, because I have this magic value. I have this number 1 that I'm initializing my mode to, because 1 means stack mode, and that's what I want to start off with. And when I'm processing, you know, an enter key, I'm going to have a statement like if mode equals 1, let's do the pop. And when I'm processing the S command, I'm going to set mode equal to 1. And it's pretty easy, middle of the night, to get confused. And, maybe think your two modes are 0 and 1 instead of 1 and 2. Or maybe think 1 is a queue and 2 is a stack. And these are things that, even if you keep them straight, they are taking brain cycles to keep them straight. They are taking concentration to not confuse these. And you don't want things to take your concentration or your energy or your time, right? Because those are your resources. So rather than spending, any energy at all trying to remember, is 1 a stack or is 1 a queue or is 0 a stack or is 2 a stack, right? You can use a pound define, and I can define a symbol like, uppercase stack, and I can define that to be a 1. And I can define queue to be a 2. And now my statement up here says, integer mode equals stack. And my statement here is if mode equals stack. And here's if mode equals queue. And the compiler, before it ever gets to your code, will before your compiler starts running, GCC will take this and run it through a preprocessor that everywhere it sees the word stack, replace it with a 1. And everywhere it sees the word queue, replace it with a 2. So this works exactly the same way, but it stops you from having to remember what these magic values were that you set up for this mode variable. And so, you come back later that night, you set an alarm for 4 a.m., you get up and start coding. How do I go into stack mode? Oh, I'll just set my mode to stack. And how do I go into queue mode? I'll set my mode to queue. And it's just one of those things that, this doesn't buy you anything that you can't do just by putting a 1 and putting a 2. But it cleans up your code, it makes your coding experience a little less painful, and it lets you, kind of concentrate on the things you want to concentrate on. And so that's a trick you can use if you haven't embraced defines yet. It's a good opportunity.
Or perhaps you could just define one of them, and then just in your if statement, you wouldn't have to have the equals sign, right?
Yeah, so you could just define a stack, and this could be if mode equals stack, and this could be an else. I guess you might still need them both when you're trying to switch modes to set what the mode value should be for both of them. But there's multiple ways you can do this. And again, this is part of kind of defining your own style, your own way of coding. If you know somebody who's been coding for a long time and you know their code, you can always spot their code. You can say, oh, Larry wrote this section of code. You can tell, sort of a signature or a fingerprint from the way people code, not just the way they name their variables or they indent things, but the way they structure the algorithms and the way they do things like this and so on. And, while you have the freedom right now to be basically writing the code however you want, within the confines of the assignment prompt, it's a really good opportunity to sort of explore the design space and find your own style. And I think that's really important, and I think it's really fun. I think it makes coding feel a lot more like your own personal creative process.
I find that I tend to pick up the habits of the first professor I had.
Yeah, I've definitely got things that my teachers have done that struck me, and a lot of those persist to today. And we're talking about almost half a century going back to my earliest coding. So yeah, those are good habits.
I feel like whatever Udemy class I'm currently on, those are my latest habits.
Oh yeah, that's cool.
One of the silly ones was I started denoting B in front of my booleans or
Oh,
defining
cool.
fake macros out.
Yeah.
Just let you know it's a out parameter.
Mm-hmm. That's cool. Yeah, and like I say, you can experiment. You can do things. If you always do camel case, you can try snake case or vice versa. And you might find something that like really appeals to you and helps you. You know, if I've got long variable names, right? I don't like variables names like, you know, k or x. So I have variable names like, you know, starburst distance, notify motion, things like that. But you know, if you type those with camel case where you uppercase, you know, the first letter of each word, or snake case where you use underscores, it can be easier to read those, and so on. So yeah, definitely explore and have fun.
But it's pretty much a given that you define constants with all uppercase, right?
Not always. That's what most people do, but I don't think that's like a universal, and it's not something I always do either. And you know, when you get to a job, a lot of times this is dictated for you. Some university classes will dictate this for you, but you know, what you do for your own stuff is your choice. And yeah, I tend to, you know, do uppercase for defines, just so that I don't mistakenly think that they're, you know, actual variables, and try to change them and so on. But
Plus, it probably helps keep you consistent throughout the code.
yeah. And consistent is hard when you're exploring and trying on new styles. You find yourself doing two different things, but one of them will win out, and that may be the one that's like, you know, resonates most closely to you. I've seen member variables usually getting an underscore in front. And underscores in front are interesting. Like a lot of tools, like compilers, will put, you know, maybe 2 or 3 underscores in front of your function name when they get converted to assembly language. With the idea being that, well, nobody's going to actually put an underscore in front of their function name, so this will make it easy to identify those. And yeah, double underscore init in Python, and all that entails. All right, so any other questions on PA2 for now? You should have enough to actually finish PA2. But again, you know, work on those functions, and you can exercise those from your own main program. Just call init, call some adds, call a print, call some more adds, call a print, call a remove, call a print, right? You can just hardwire those things together and get, you know, a good feel for how your code is working. Just like what I did for testing some of your code, right? So I just made a main program like this. There's no user interaction, there's nothing to type, there's no parsing. I just called a bunch of functions. Call init, call a print, call a bunch of adds, call some more prints, searches, and so on, right? And you can make your own test script like this, and it's so much faster than, you know, typing in your commands and trying to remember what your output should look like and so on. And then, you know, once you feel like your linked list package is working, then you can start putting together your main program. But, you know, whatever order makes sense. You should have everything you need to be able to do all the pieces of this now. So I would suggest, you know, starting it sooner as opposed to later, even though you've got, you know, a week and a day to get it done. If you always do this at the last minute, and it only takes you, you know, a day, my suggestion would be make yourself an artificial deadline. Just say this is due Tuesday morning at 8, and make that your deadline in your head and get it done by then. And then if something comes up, it's a lot harder than you thought, or you know, something changes in your schedule, you've got some wiggle room there. And that's probably better than using slip days.
Yeah, I gotta say, I looked at this yesterday and it seemed a little daunting, but after talking about it today, it seems to be not too bad.
Yeah, I think it's definitely doable if you break it down and don't get overwhelmed by the sheer volume of instructions, because a lot of it's just keeping the pieces straight.
I think seeing there should be 11 functions. I was like, what?
Right.
Like, but actually, they're all pretty simple.
Right. All right, well, let's go on and talk about hashes. And hashes will be your third programming assignment will involve hashes. So we're going to start this early and build it up. And hashes are another type of data structure, and they're a way to store information and retrieve information. And hashes are largely about performance. So, an array, we've got order 1, order n, maybe order log n for doing certain operations. And we didn't like that order n for insert and delete. So we created linked lists where you can insert something in the middle without having to move things around and such. Let's see, I have a question. How can I initialize an empty linked list? Temp equals malloc, temp data equals 0, temp next node equals null, return temp. Yep. That's exactly how you initialize an empty linked list. Yep, you're welcome. All right, so linked lists are a little better performance-wise, but to find a node, we still have to move linearly in its order n, and eventually we'll turn our lists into binary trees, and binary trees will give us nice log n behavior for search, for insert, for delete. But a hash is even better. Theoretical performance for a hash is order 1. So what does order 1 mean? It means if you have 10 things in your hash and you want to add, you want to search, you want to delete, it takes you a certain amount of time. If you have 10 million things in your hash, those functions take the same amount of time as if you only have a few things. You can add more and more data to a hash, and theoretically your performance does not change. And that's really nice, especially if your name is Google. And you're starting off with a few web pages today, and in 20 years you're going to have trillions of web pages to serve. It would be nice if searching didn't become a trillion times slower, or a trillion squared times slower, right? So order 1 is really nice, and it's not perfectly achievable, but theoretically it is.
So when you say theoretically, you mean if coded correctly, right?
If the description of a hash, the way it works in theory, will be order 1. But in practical terms, at some point, the performance of a hash will start to degrade. And we'll see exactly why in a little bit. So this is related to associative arrays. And so remember, with a plain array, integer data, bracket 10, we have 10 spots in memory, and we have somewhere in memory that our array begins, and let's just say this is integers that take 4 bytes to store. And so if we say data bracket 3 equals 17 0 1 2 3, right here we're going to store the binary code for integer 17. And if we say data bracket 0 equals 42, well, element 0 is right here in the beginning, so we're going to store 42 right there. So this is a plain old array that we've been using, since like probably CSE222 or before. And the reason that, we can store things wherever we want in a fixed amount of time and retrieve things in a fixed amount of time is because there's a fixed mapping. If we say data bracket I, there's a formula we can use to figure out exactly where in memory this number is stored. And data bracket I is stored at memory location. Well, it's the address of data bracket 0. It's wherever this first memory is, plus, in this case, 4 times I. And it's 4 times I because each integer takes 4 bytes. So if this was stored, at location 100, this would be location 104, 108, 112. So where is data bracket 3 stored? The address of the first element, which is 100, plus 4 times 3 is 12. It's at location 112. And so in your C program, if you say something like data bracket I, and you look at the assembly language, there's something in there that's taking your index I, multiplying it by the length of an integer, adding it to the address where your array begins. It's a fixed map. And so we have this function that you feed the index in, and it gives you the address in memory where data bracket I is, or where data bracket index is. Alright, that's a plain old array. Let's remember what an associative array is. An associative array is like this, except your indices don't have to be integers. So let's say I have an associative array. And let me just call it data. Well, I can do things like data bracket hello, or data bracket, and I can make a string, this is weird. Or I gotta have data bracket, 3.1415927. I can index this array with things other than consecutive integers starting from 0. And the way that we're going to build this associative array, which is what a hash table is, we're going to build these from scratch in C. The way that we can implement an associative array like this is exactly the same thing as what we do with a plain array. We're going to take our index, we're going to feed it into some magic function, and it's going to tell us where is that data. And as long as this function, doesn't somehow depend on the amount of data stored in our array, this is going to be order 1. So this function is called a hash function. And its job is to take an index and tell me where that data element is stored, the element with that index. Or, if I don't have an element indexed with hello, it should tell me that. So for a plain array, this hash function is straightforward. Just take the address where the array begins, add your index times the size of each thing in your array. So integers multiply by 4, doubles multiply by 8, and so on. The hash function here is a little trickier. Alright, so that's the basic setup. So maybe the next question is, why would we want to do this? Why do we care about associative arrays? And how do they help us do things like fast search, fast insert, fast delete? Well, insert's not so mysterious, right? If I want to store a new piece of data, I run the index through my hash function. It tells me where in memory to store my data. I just copy my data over there. So insert's going to be fast. But how does this help us with search or with delete? Because if we don't know, where something is stored, how do we index it? So this is the associative part. So let's think about an example. Suppose we want to store the following information: a license plate plus the name of the person who that plate is given to. So we're making a database of license plates. And we could do this with a pair of arrays, one array of license plate, one array of names. And then if we want to find the license plate corresponding to, ABC123, we search through this array for ABC123, and when we find it in element, 97, well, we just take element 97 from the name array, that's the name associated with that plate. But, searching for license plate ABC123, that's an order n operation. the bigger our array, the longer that might take. And if we alphabetize it, we can cut it in half and do order log n, but then to insert something becomes order n. And if we used a pair of linked lists, we could insert more quickly, but it still takes order n to search and so on. So we could do this with what we already know, but it's not very efficient. So here's what we're going to do. We're going to make an associative array. Also called a hash. Named, let me just call it data. And let's put some information about plates and names into our array. So suppose I know that ABC123 is the license plate of some joker called Nick, right? So here's what I'm going to do. I'm going to say data, and I'm going to use that plate as an index, and I'm going to store Nick in there. Okay, this is obviously pseudocode. It's not C, because you can't do this in C. But at the index given by that license plate, I'm going to store the name of the person who owns it. And maybe, license plate EE-456, maybe that's Izad's license plate. So I'll store Izad in the database at that index. And so I can start storing information about license plates in here by simply associating a name with a license plate. So if there's a license plate called haha, and that's the joker's license plate, right, I could store this.
And that just sets haha to joker, right? Like not the other way around. Like if you looked up data joker, it wouldn't print out haha.
Correct, yeah. This is an index. This is the data stored at that index.
Okay.
So now if I see a license plate like ABC123 and I want to know who does that belong to, all I have to do is look for data bracket, that license plate, and it should give me that name.
And briefly touched on this in 215, but are we going to go over how this gets stored in the hash table?
Definitely.
And how the data actually, okay.
Yeah, because we're going to actually implement this. So we're going to have to understand how this is, the mechanics behind this.
Cool.
So the idea, though, is, you want to know who owns a license plate ABC123, or we're going to put that string into this function, and it's going to give us back, effectively a memory location, and then we're going to use that memory location to, just read out the name associated with that. So this is why a hash is going to be order 1. Because we can search for, we might have a million license plates in here, but if taking the plate gives us the exact location where this name is stored, we just go to that location and read the name. And there's no searching involved. And since you can retrieve, the associated data without searching, that's a fixed amount of time, regardless of the amount of data. That's order 1. And that's our ideal, close to our ideal performance. All right, good so far?
Yep.
So the next question is, how does this hash function work? How do we actually do this mapping from an index to a location where our data is stored? And it's a little bit of magic, but mostly it's just math. So here's an example. We could take ABC123 and add the ASCII code of each character. And when you get some number, right? Each ASCII code is, roughly no bigger than 100. So if we have 7 characters in a license plate, it's not going to come out to be something bigger than 700, right? And so we're going to make a big array. And let's just say, this array is going to store 1,000 names. So 1,000 names. So when we get a license plate, we're going to add up the ASCII code for each character in that license plate. It's going to give us a number between, 0 and 999. We're going to use that to tell us where we should store the name associated with that plate. So I don't know what you get when you add ABC-123, but let's just suppose you end up with this number down here. That's where I'm going to store the data for ABC123, which is Nick. So I'm going to store the name Nick in here.
So what happens if you have ACB-123? It would come up with the same number.
Oh, that's a problem, isn't it? So yeah, we'll get there in a second. Let me do 2 more of these. So let's suppose what was Izad's plate? 456. Let's say that maps right here. So that's where we store Izad. And let's say haha. That's a short plate, so maybe that maps right here. So that's where we store the Joker. So yeah, so what if we do ACB-123? If I add up the ASCII codes, I'm going to get the same thing as if I add the ASCII codes for here. This is going to want to point to that same spot. And that's a problem. So this is something called a collision. And a collision happens when this magic hash function is taking 2 different things and trying to map it to the same spot. So if you've done discrete structures, well, we've already done it in both classes actually. This is great if the function is injective, if different indices map to different locations. But when 2 indices map to the same location, when this stops being injective, we've got a collision. Because now, what should I store here? The name associated with that plate or the name associated with that plate? And so collisions are where hashes stop working the way they work theoretically. And this is where we start taking a performance hit.
So, in practice, wouldn't the hash function do some kind of parsing to realize, oh, there are quotations around this thing. These 2 things should probably not point at the same thing?
Yeah, I didn't mean to put those in there. But yeah, the hash function needs to, it would presumably dutifully take whatever string you pass to it, whether it had quotations or not. If it had quotations, it would add those in also. But I didn't mean to put quotes there and not here.
So, what exactly do you mean by it's taking all these ASCII codes and finding what they add up to store something in the array? I'm still a little confused on that.
So here's a sample hash function like the one we're talking about. Set a running sum to 0, go through each character in your string and just add its ASCII code to that running sum. And so this, can just return sum. This is a function that gives you an integer. So if I hash, ABC, it's going to give me back 65 plus 66 plus 67, the ASCII codes for that. And whatever I get back from the hash function, right, assuming it's between 0 and 1,000, I'm going to use that as an index to figure out where in this array of names I'm going to store the name associated with that plate.
So that's how you can run into collisions. If you just get the same addition result for different ASCII characters.
Exactly. And one way to do that would be, you know, just transposing the order of the characters, because the order doesn't matter. So ABC and ACB will add up to the same thing.
I'm assuming there's some ways to avoid that, right?
Yeah, so collision management is a whole science, and it depends largely on the nature of your data. And so, for example, you know, if you had names, there's not a lot of names where transposing 2 letters gives you another valid name. So if my index was going to be a name, it might not make a difference. If my index is going to be a license plate, well, there's lots of cases where, you know, I'm going to have ABC123, I'm going to have ABC132, right? So that's probably going to give me a lot of collisions. So you can start doing different things. For example,
what if every time you went through that for loop, you took the index and you also added it? So that way, like, if you do ABC, it would add the ASCII code for A plus 1, and then the ASCII code for B plus 2, and then the ASCII code for C plus 3.
So
In any order, right?
I see what you're trying to do. That actually won't help because addition is commutative. And you would be adding the ASCII code C plus 2 and B plus 3. That's going to be the same as adding ASCII code of B plus 2 and C plus 3.
Oh yeah, that's right.
But good idea. And for example, instead of adding, you could multiply by, you know, I plus 1. And now the position in which each ASCII code occurs will change the sum. Because this would be B times 2 plus C times 3 as opposed to B times 3 plus C times 2. So you can start perturbing your hash functions, and there's a whole, you know, discipline to coming up with good hash functions, depending on the nature of the data, and so on and so forth. And there's lots of ways to make hash functions. So sometimes, you know, you might just, if you were hashing student IDs, you could just pick the last 3 digits of the student ID, right? And that's a reasonable hash function. If you decided to pick the first 3 digits of the student ID, that's a terrible hash functions. Because most student IDs start with, you know, 101 or 201. And so you get tons of collisions. So if you know something about the nature of the data, that can help you come up with a better hash function. But the reality is, collisions are inevitable. Because my array is only going to hold so much stuff. And if I have more than 1,000 license plates, and I only have 1,000 places to store 1,000 names, I'm going to have collisions. Anybody remember what that's called from CSE215? We haven't done it this quarter yet, but we did in fall. If you've got more than 1,000 names to store in this array that only holds 1,000 things, why are you going to have collisions?
Oh, pigeonhole concept.
That's the pigeonhole principle, right?
There you go.
So it's a thing.
Yeah.
So you're guaranteed collisions will happen just because the space of things that you're putting into your array is so much bigger. And I mean,
seems like a problem. If you're trying to do that collision management in some way or another, it seems like you'd be scattering the data randomly around the array where you'd have spaces of like nothing being stored and things being stored.
yeah.
And then it seems like you'd run into that pigeonhole concept where collisions faster that way because you're just randomly scattering out the data.
Yeah, and that's another part of choosing a good hash function is avoiding what we call clustering, where you get, you know, a whole bunch of data right here and a whole bunch of data right here and a bunch of empty space in the middle. And again, if you know something about the nature of the data, you can choose a hash function that will help minimize that. And so, you know, using the first 3 digits of a student ID is a classic bad choice for a hash function, because all your student IDs will map to one of 2 locations. If your IDs always start with, you know, one of 2 sets of 3 digits. Or phone numbers, if you try to use the first 3 digits, that's just the area code. There's not a lot of variability. But no matter how clever you are, right, you're going to have collisions. And you're going to have a case where you have two indices trying to use the same location in your array. And you got to have a way to deal with that. And there's a variety of ways to deal with it. One way is to use something called probing, which we'll talk about in some detail next week. Another way is to use, guess what, a linked list. And instead of storing the actual data here, we store a pointer to a sentinel node, and then in each list in that node we store a name. And if we have another name associated with ACB123, maybe that's, you know, somebody else, well, we just keep adding these into a linked list. Now, linked lists are not order 1. But if you only expect, you know, 3 or 4 collisions, well, you know, you use your hash function order 1, you find the linked list to search, and that linked list only has 3 or 4 things in it at most. It's not that bad performance-wise.
Or
So,
perhaps a second hash function.
or a second hash function. So this is something called chaining. And that's probably the approach we're going to use when we implement hash tables for PA3. And it will let us reuse our linked list code yet again. So we'll get a lot of mileage out of PA1. But you can also do this idea of probing, which is use a different hash function. And so if this gave me a collision, well, I'll run this through a different hash function and hopefully get a different location that's available. And you can keep rehashing with different functions until you find a spot that's free.
Or even maybe just jump to the next available spot.
Or you can just jump to the next available spot, and that's one version of probing. Is, you know, your next hash function would simply be your original hash function, but it would add 1 to the result. And your next hash function would be the original, but it would add 2 to the result. And the idea is, you know, you come down to the next available spot.
That's what I was thinking, but it seems like you'd have more computational power to try to, like, decipher that and then store something in the array.
It's not a bad performance, though, as long as you can avoid clustering. Now, there's a possibility that if lots of things are all pointing to the same spot, and you just decide to store in the next available spot, well, you're going to get a clustering effect. And so if you use a hash function that on the next hash attempt doesn't just go to the next spot, but uses something about this to come up with a different location, right, those two things that collide might, on their second hash attempt, go to very different locations. And then you get a more, you know, spread out behavior of your collision resolution. And this is details that we're not going to worry about too much. We're gonna be given a hash function for PA3, and we'll use that, and we'll be told how to deal with collisions, which will probably be chaining through a linked list. But if you were, you know, trying to implement your own hash function for something proprietary, right, all of these things would be concerns you'd have to deal with. And it can get super theoretical. It can get into all kinds of statistics and trying to analyze, you know, average case performance, worst case, that kind of thing. That's all its own set of fun challenges. All right, so some terminology, and we're going to wrap up soon here. So we usually identify these things not as indices, but we usually think of this as a key data pair. So this thing that we're using in here is considered the key, and the thing associated with it is considered the data. And so we use the key to access this hash, and we retrieve a piece of data associated with that key. That's the association part of an associative array. We did this in 224.
Asynchronous arrays or something.
Yeah, when we were trying to count how many times phrases occurred in a set of input. And so the way we implemented that was we made an associative array, and we used as a key the phrase that we were trying to tally, and as a data the number of times we'd seen that phrase. And so, if we were tallying how many times we saw ha, 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 well, data bracket ha, ha would be initialized to 1. The next time you see ha, ha, we would read this, see the 1 incremented to a 2. And so in this associative array, we're storing these key data pairs. The keys are the phrases, the data is the number of times we've seen that phrase. And the implementation of associative arrays in Bash is super efficient. So we could have lots of things stored, and if we go in with a phrase, it can pull up that tally very quickly. And we can bump it up by 1 if we just saw the phrase again and store it back in the array. And it's all pretty efficient. And again, worth mentioning that like associative memory is to some degree probably tied into how human memory works. Right? When you hear a song lyric, you don't begin a sequential search through every memory in your brain trying to figure out where you heard that song. Right? Or when you catch a scent walking around outside, you don't start going through every memory in your brain and try to think, where did I smell that? Right? What happens more often is you hear a song you haven't heard in 20 years, and suddenly you remember, something from your childhood. Or you catch a whiff, and suddenly you remember something from, when you were 16, walking around outside with a friend. And that's not happening by sequentially searching, a set of data or following nodes from one to the next, like a linked list of memories. There's some sort of associative structure where this thing that just came in, this piece of a song lyric, this scent, is somehow being used to access data and pulling something out of that, and then this thing that you pull out is maybe being used to access the data again. And you're sort of building this like associative chain of memories that get you from, something to something surprising. And so there's cognitive theory that, considers human memory to be associative in nature, and it's arguably part of where intelligence emerges from, is that kind of organizational structure. All right, so that's bonus for the 12 people who are here. Someone says, Algorithms to Live By Brian Christian talks a lot about data structures in everyday life. That does sound amazing. I'll have to check that out. Because, a lot of this stuff, this didn't come down from just kind of randomness. A lot of the algorithms that have been developed, a lot of the data structures that have been developed are based on, our sort of daily experience, our real world experience. And so they map nicely to a lot of things that you find in the physical world. All right, so where does this leave us? We need to talk about hashes as an abstract data type. So what's the usual interaction to a hash? And it's basically, store something, retrieve something, search for something, those kinds of things. So we'll talk about that, and then I want to start digging into details of how we actually implement this. And we've got a good start on it with this, right? Using a hash function to take the key and find an index for data. And then we just need to figure out what we're going to do with collisions. So I want to spell out some of the details for these different approaches to collision management for chaining, which is pretty straightforward, and for probing, which can be more complex. And then we're in good shape to start thinking about how we actually code this. And so we'll talk about that, and in a couple of weeks we'll get to PA3, and we'll actually start writing code to make an associative array and use it for probably a database of license plates. So that's where we're heading. I'm going to let you out 3 minutes early because it's our Friday, because it's Thursday, and then I want to start on something very different. So have a good weekend. Come by office hours tomorrow at 9 if you've got any questions on this. If you get started on PA2 and you're running into issues, come by office and we can work on it there. If I don't see you, have a great weekend, and I will catch you next week. All right, thank you.
Thanks for everything.
Thank you. Have a great weekend.
Thank you.
Thanks, you too.